Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Field. So, in fact, for concreteness, maybe the rationals or just function field over a finite field. And so on K, we have the usual collection of absolute values. Normalized by the product formula on the non-zero elements. So the product equals 1 for all non-zero elements in the field. So in the rational case, you use the usual absolute value in the p-adic ones. And in this case, you'd have the degree absolute value at infinity and the usual pi-adic ones for the various irreducibles pi in kappa bracket u. And so this allows us to talk about, this defines the notion of height. On points of projective space over k bar. And so, for example, if you just take a point x0, xn, let's say in projective space over the rational function field, then you just clear denominators so that these are polynomials. Maybe I should call them g's, right? And if you take these to be the gj's, to be actually, maybe I'll make this more concrete. Sorry. So for example, if I give you a point x0 through xn in Pn over the rationals, then the height, if you clear these so the xi's are integers with GCD 1, then the height of this point, P, height of P, is just the max of the absolute values of the xj's. This is the usual Archimedean absolute value. And similarly, if you were in projective space over this doodad here, then these would be rational functions. You'd clear the denominators to make these into polynomials with no common GCD, and then you take the max of the degrees of those things, essentially. The important point is that there are only, let's say if you're over capital K, as opposed to k bar, if you put a bound on the height, there are only finitely many points. So when we're interested in asymptotic questions over global fields, maybe where things are parameterized by points of a projective space, we might sample over points of height up to something, do a count, and then kind of let the bound go to infinity. OK. So now let me introduce the sort of thing we're going to want to contemplate. So we're going to think about, I'll call it E eta, will be an elliptic curve over k of t. So we could think, for example, for, let's say, not in characteristics 2 or 3, we could think about this as y squared equals x cubed plus a of t x plus b of t. And then if I give you any particular element, little t in k, avoiding the denominators of these rational functions, then we likewise get a specialization e sub t, y squared equals x cubed plus atx plus b of t. And this will be an elliptic curve over k, provided, again, we avoid finitely many more values to make sure that the discriminant is not 0. So for all but finitely many elements of capital K, you can substitute in and get a specialized elliptic curve. And so we think of this as sort of a family of elliptic curves over K. In the sense that you can write down an equation with a parameter, and as the parameter varies through capital K, then we get a whole collection of elliptic curves given by a formula whose coefficients depend algebraically on the parameter as dictated by these two functions here. And the question that is quite natural to consider in this context is, to what extent is the group of rational points of the members of the family somehow described by solutions at this level here? which is to say, for example, is it the case, or how often is it the case, that in fact you can give an algebraic formula for all the rational points, perhaps maybe up to a finite index. So let me say that a little bit in a slightly more geometric language, which will be convenient for our purposes. So you start off with P1, and then you can actually make what's called an elliptic surface. I won't do anything specific with this for today, although technically it's hiding in the background. So this is some formula over k of t, and if you clear denominators in the right way, for most values of t, you'll have your, so at most points t, then you have e sub t. But then there'll be maybe some bad values where when you try to specialize, maybe the discriminant will vanish, some kind of weirdness may happen. So you may have, for some special values, maybe t0, t1, when you specialize, the equation could have singularities or be something pretty awful. But most of the time, that's not a problem. And so if I give you a point, if I give you a solution, if I give you a solution to the equations in terms of rational functions, you can try to specialize and get a point at t. And this group here, well, this is finitely generated by the Mordell-Weil theorem, but this is also finitely generated. This is the so-called Lang-Neron theorem. Although strictly speaking, this version is due to Neron. It's in his thesis. So this is a group. This is a group of solutions and rational functions. This has finitely many generators. Each of those generators you write in terms of coordinates with rational functions. They have only so much denominator going on. And so as long as you avoid those denominators, you can specialize away, and there's no ambiguity about what's going on. Similarly, when you try to add points in the algebraic formulas for how you add in the group law. So in this way, we get a map from this group to this group. And the question that I'd like to discuss is roti, well, maybe we should ignore torsion. So we'll take the Mordell-Weil group and just think about, on the level of rational vector spaces, is this an isomorphism for most t? Or not? Okay, so that's the question we'd like to consider. Now, an important fact, so this is from Silverman's thesis, so we'll call Silverman's specialization theorem. Which says that in this context here, with only finitely many exceptions, this is injective. Okay? For all but finitely many t, in fact, he says something slightly stronger. There exists some constant b, so that if t is a point, maybe not even in k, just some geometric point, and the height of t is bigger than b, then the specialization map from the rational function solutions to the group of points on the fiber is injective. In particular, suppose you thought about only those points for which the height, for which t is actually a k point. Let's assume t is a k point. Then there are only finitely many points with height below b. So this ignores only finitely many t's. Okay? So the upshot is that if you consider this thing, then for all but finitely many t, rho t is injective.
Is this before tensoring with Q?
Okay. Yeah, this is before tensoring with Q. And so in that context, the one that I set up here, this, if you ignore finitely many, these will always be injective. And so the real question is just you have an a priori inequality. So this is really, i.e., It's a question of ranks. When is the rank of this equal to the rank of this? Okay? That's the real question. I'm not claiming to get the full Mordell-Weil group on the node is a very strong request, but could you at least account for the size, for the rank of it, just coming from formulas in rational functions? Okay? Oh yeah, the big B depends upon the particular elliptic curve as well. It's not a special universal constant. It depends on the particular elliptic curve, the particular E eta that you choose.
Is it giantly big or small?
It's a completely abstract constraint.
Nobody knows any bounds.
To be honest, I did read Silverman's paper, but I'm sure that in the case, he proves it for abelian varieties, and I'm sure in the case of elliptic curves, one probably could go through his proof and make it explicit. But then again, actually, yeah, it's slightly tricky because it comes out of knowing, you know abstractly that this is finitely generated, and you first define a height pairing here, and you have something that's a non-vanishing determinant of a height pairing, and you have to have that number. So I suspect to compute the number, you'd first have to find a basis for the Mordell-Weil group of this. So it's probably a little bit hard to compute. But. OK, so that's the basic question that I would like to contemplate. And so let me make a definition. So the thing we would like to consider is, to what extent is it the case that the rank on the special fibers for the little t's is in fact fully accounted for by the rank generically over k of capital T? Right? Can we give a sort of an algebraic formula for a basis of the Mordell-Weil group on many of the fibers or not? So let's give this, I'd like to give this a name. And we'll say that the elliptic curve has elevated rank if this doesn't work most of the time. So I'll just make a definition. Let's say that this elliptic curve over k of t, k of capital T, has elevated rank if, in fact, roti tensor Q is not an isomorphism, is not surjective, in other words, for all but finitely many T. Okay? So in other words, what it's saying is, on most of the fibers, there are going to be kind of extra points of infinite order that aren't accounted for by formulas. All right? So I'll give you I'll give you an example of this. So where's the explicit? This is an example due to Rohrlich. Here it is. So in the case of the rationals, well, actually, the examples are all conditional. Pick your favorite positive integer that's square-free and congruent to 7 mod 8, such as 7, for example. And you consider this elliptic curve equals x cubed minus x over q of t. And call this E eta. And in fact, this example is due to Castles and Schinzel. That E eta of q of t actually has rank 0. So they check this. That the only solutions in q of t are, in fact, points of finite order, and they found them. On the other hand, if you look at for all rational numbers, so this thing has positive rank if you believe the Birch-Swinnerton-Dyer conjecture. More specifically, you believe the parity conjecture. What do I mean by that? For any elliptic curve over a number field or a global field, there's a sign attached to it called the root number. Okay? So you can define a sign called W of ET. It's a sign plus or minus 1. It can be defined by representation theory method. And it's known that if the L function of the elliptic curve has nice functional equation, analytic continuation, for example,
over the rational numbers, this follows from the modularity of elliptic curves, over rational function fields, any global function field, this is a theorem of Deligne and Drinfeld, that if the L function elliptic curve has a good functional equation, then this number that one can actually compute in any particular case is the sign of the functional equation. So this should give you, so if you believe that this root number computes the parity -1 to the rank. If you believe this fact, right, the key point is that the W's or the ET's are all -1. Okay? So this family that I've written down here, if you plug in various rational numbers for this, you can actually calculate the root. This is a family of quadratic twists. Of the curve y squared equals x cubed minus x. And there are actually formulas. There are completely explicit formulas that say how the root number changes if you make a quadratic twist in your elliptic curve. And so if you stare at these formulas and you twist by the right kind of algebraic expression, then you can just rig it so that it always comes out with a fixed sign. In this case, they rigged it carefully to always come out -1. And the trick was to do it in such a way that they could guarantee the generic fiber had rank of kind of the opposite parity, which is to say, this says that if you believe these million-dollar problems, well, if you believe that they're true, then the parity should be odd, but yet the generic fiber has rank 0, and so therefore, on all of these fibers, there should be these extra points of infinite order. Okay?
You also want the rank of E if Q itself.
Well, so no. All you would know is that it should be odd, but of course, one has no way of writing down points in a kind of a general sense in that there's not going to be an algebraic formula. If you could find an algebraic formula for a point of infinite order, well, I don't know what you mean by algebraic, but the only thing I can think of is something in here. And, well, there are no such things of infinite order by the Silverman specialization theorem applied to this example. So there is this kind of conditional example, and Rohrlich showed that, in fact, for any elliptic curve over Q, not just these guys, you can always do an analog of this kind of device. You can find some way to make a quadratic twist so that this thing has rank 0, and yet, by being clever, all the fibers have root number -1, and so somehow in every fiber there's like this extra point of infinite order. Where is it? Can't find it. All right. So the question that we thought about was the following. Geometrically, these kinds of examples feel kind of fake. Well, they're not fake. I mean, they're there. But the point is, they're families of quadratic twists, so-called isotrivial family. Okay? It's just quadratic twists. And you would like to ask, is it possible that one could make situations where it's not just given by quadratic twists? And this is a much harder problem in the sense that the behavior of the root number in the fibers is very complicated when they're not just related by simple twisting procedure. So now let me tell you a fact that comes out of Helfgott's thesis. If you think about families of elliptic curves that over Q of t, maybe I should mention one other fact. There's another standard conjecture called the density conjecture. So standard conjecture, density conjecture. Which is the following belief that for all points t away from a set of what you might call height density 0, what do I mean by height density? If I give you a set of points, then you might consider the set of elements in your set up to height b divided by the total elements of height up to b, take the limit as b goes to infinity. Okay, that's what we call the height density. All right. So for the belief is that for all points away from a set of height density 0, that in fact the rank on the fiber should be the generic rank or +1 determined by the sign, or the rank +1. And then these, of course, would be distinguished by knowing the root number. Okay? So the belief is that most of the time, in fact, if you have the root number could sometimes force the rank to be higher than your original situation if the parity is off. You might have to have something extra. Okay? But the belief is that most of the time, if you have anything extra, it'll be at most one thing more. And so if you believe this, if one believes this, if you believe the density and parity conjectures, the parity conjecture is this thing that I said down here, that it's this one here. Is the root number really minus 1 to the rank? If you believe Birch and Swinnerton Dyer, this is true, but this is, strictly speaking, a weaker statement. If one believes these conjectures and one other conjecture in analytic number theory, I'll tell you what that conjecture is right now. Roughly speaking, it's the following belief, that if you have any polynomial, take n up to x, divide by x, this goes to 0 for any polynomial such that plus or minus f is not a square. Or square free, I should say. So if I give you any polynomial that has no square factors, plus or minus f, just say f has no square factors. So there's no obvious, so mu here I mean the Mobius function. Okay? That if you average the Mobius function on a polynomial up to x, take the average value, that it should die off asymptotically. How often does f of n have an even number of prime factors versus an odd number of prime factors? That there's no obvious reason to have preference either way. So the belief is it averages out to 0. This is of course, this has never been proved, even in the case of a linear, in the case of a linear polynomial, this sort of thing is, well, at least quadratic, maybe linear too. I think even the linear case is not known. But anyway, so if one believes these things, here's a fact that comes out of Helfgott's thesis, that any elliptic curve over Q of t with elevated rank must be of this sort, isotrivial. Meaning it must be a family of quadratic twists, well, and which is this, what I really mean here is that the J invariant has nothing to do with t. So strictly speaking, it could be a family of cubic or sextic or quartic twists for some special values of J. But essentially, the point is, if one believes certain standard conjectures, that in fact over the rational numbers, this sort of trick construction that exploits the fact that root numbers and quadratic twists can be computed explicitly, this is the only way to make such constructions. Now here's the interesting point. The analog of this conjecture in the case of K of U for a finite field K is false. Completely false. There are counterexamples to this.
What is false? Say it again.
What is false is, so there's this heuristic belief that if a polynomial has no obvious reason to have square factors for algebraic purposes, right? Let's say it's like an irreducible polynomial, right? Then the belief is that Mobius averages to 0. But now you consider the analog in the function field situation. Suppose I give you f in KUT, right? I'm two variable polynomial of a finite field. Let's say for concreteness, it's irreducible over K of U. And what you might want to believe, or one might imagine, is you take f, all right, f of u comma g of u. You plug in for t elements of the coefficient ring, like here we plug in for n. And now you take Mobius of this sucker, okay? And then you average this out, take the sort of the average of this thing over g's of degree up to n. And one might ask if this goes to 0. And in fact, this is false. It's actually quite surprising that, but this is a story for another day. So this is in fact false, that there are unexpected things that happen. And what it suggests is the possibility that one should reconsider this question. Is it possible that in the function field case, there actually do exist non-isotrivial families for which the, for which there's this discrepancy, there's elevated rank? And I should say the key point is the following in terms of where this is coming from. in general, if I give you a family of elliptic curves and you try to study the relationship, the variation in the root numbers, what tends to happen when you're not in this situation, when the J invariant actually has denominator, okay? If it's not just or even has a numerator, if it has zeros or poles, okay, if it's not a constant, then it turns out when you try to study how the root numbers vary in the fibers, you wind up having to compute the Mobius function of the numerator and denominator polynomials evaluated at specific points. And to the extent that that effect averages out to 0, then one gets this prediction. But given that there are situations where these things don't average to 0, although I'm not claiming that the counterexamples to this in any obvious way come from elliptic curves, that they arise out of J invariants of some construction, but at least it opens the possibility that maybe one could find situations with such a counterexample to relate it to this argument. So now let me write down a very explicit elliptic curve. So this is, in some sense, the whole point of the talk, is to sort of discuss a particular example.
Sorry, Ryan.
Yes?
When you say counterexample, you're talking about in the characteristic P case?
Yes.
Okay.
Yeah, because here I said that if you believe,
Yeah.
there's no reason to believe that any of these conjectures are false,
Okay.
as far as anybody knows. They could be false. Who knows? So now let me write down a very explicit elliptic curve. So, an example. So here's one. Maybe to get this started off, let me write down something. So let P be an odd prime. And let's consider the following elliptic curve. I'll begin with, I'll call script E. Y squared equals x cubed plus, I need another letter here. Let's say ax squared minus a cubed x. And consider this is over the field fp of a. Okay. This is some elliptic curve. And one can calculate the J invariant this thing, and it's non-constant. It really involves the parameter a. Right?
A is indeterminate?
Yeah, a is an indeterminate. Okay. And there are a couple of obvious points on this. I'll just write down one of them. I'll call this capital Q minus a squared. Right? If you plug in a for x, then these two something should something cancels out. Minus a for x, then this becomes minus a cubed. This is plus a cubed. So these cancel out, and this is this is a to the fourth. Good. Yeah. So this is on the curve, and the point is, and in fact, one can check by using an analog adapted to characteristic P of the classical Nagel-Lutz criterion for a point of finite order. One can actually check that if you multiply this point by 4, this actually has denominator, has non-trivial denominator. And one can exploit this. Right, the Nagel-Lutz theorem says that one point is that for an elliptic curve of Q, if a point actually is not integral, it must have infinite order. Okay? And there's an analog here, and you can use this. Well, this really applies to here, that in fact Q has infinite order. Okay? So this elliptic curve does in fact have positive rank. And now we're gonna make the example. So here's the example. So let's let.
How about the point 0, 0?
Yes. So the point 0, 0 differs from this by the point 0, 0 is 2 torsion. Okay? And there is a third obvious point if you think about it, which turns out to just be this thing plus 0, 0. So there are a few points, but 0, 0 has order 2. So that's not going to help. All right, so here's the example. So let's say kappa over fp is a finite extension, any finite field. Take it to be fp if you like. Capital K will be, we'll take to be kappa of u. And now here we go. And let's choose some constants, C and D. You could take them to be 1 if you like. And here's the construction. We take E eta over K of t to be obtained from this guy by extending scalars. We're going to stuff FPA into K of t by sending A to the following slightly yucky expression. C times t squared plus u to the 2p plus d times u. It kind of mixes up t and u, so it's a little bit yucky. So it's y squared equals x cubed plus this yucky thing. Of course, that p power, it turns out, is in there for a reason. X squared minus this yucky thing again, x. Okay? So that's our elliptic curve over k of t. And again, k of t is just really rational function field in two variables, if you like. And, well, we had a point of infinite order, and so if we extend the base field, it still has infinite order. Okay? So there is some explicit point of infinite order. And now I'll state the theorem. So we have one point of infinite order. And it's non-isotrivial. If you compute the J invariant, it involves capital A in the first case. So when you make this yucky extension, it's even yuckier. It involves both u and t. It's a big mess. Okay? So this is not isotrivial. So this is not a family of twists. Okay? So it doesn't have constant J invariant relative to the base field. So here's the theorem. And I'll just sort of say a few things about how the proof goes. So theorem is two parts. That, in fact, there's nothing extra in the rank. The rank is 1 on the nose. But for all points t in P1k, well, away from infinity, let's say. So again, here you should think about t concretely as this is just an element of k. You think about t as a ratio, kind of f of u over g of u, where f and g are just polynomials, and they're relatively prime. Okay? So for any value that you plug in, for all such points t, the root number of the fiber is, in fact, well, whatever's the opposite. This is odd, so it's plus 1. I guess it should be, yeah. So therefore, it has elevated rank under the parity conjecture. Okay. Now, so what's this? So again, just to recap, the point of the example is over the rational numbers, examples of this type are not supposed to exist. If you believe these sort of BSD, parity conjecture, this density conjecture, that most of the time, if the rank of the special fiber is bigger, it should only be bigger by whatever is determined by the root number, plus 1. And if you believe this thing about the averages of Mobius, over the rationals, there are supposed to be no examples of this sort. And the whole point is that because one of those conjectures fails, it suggests the possibility, and the whole point here is that it really happens, that this particular elliptic curve, which we see does have an explicit point of infinite order. Just plug in this yucky thing into A, and that gives a point on here. The crux is that I claim, this is actually the hard part, that there's nothing extra over here, and yet all the specializations actually have root number plus 1. And so if you believe the parity conjecture, these should all have even rank. And yet, this thing has a point of infinite order. And there's an analog of Silverman specialization, that when you specialize the point of infinite order here to the fibers, most of the time it will still have infinite order. So these things do have positive rank. And so the content of this would be, the point is that the rank of these guys are supposed to be even, but yet positive because of that. So therefore, it would have to be at least 2. Okay, so there'd be something extra. Right? So that's sort of the point of the theorem. And so now let me just make a couple of comments before I discuss what I think is the most interesting part of the proof. So there are really two different parts of the proof. One is to actually pull off this calculation. And this, I should emphasize, this is the sort of calculation that is absolutely impossible to do over the rational numbers. Okay? Precisely because when you try to write it down, that involves this Mobius of a varying quantity. And there's just no way to, you look at even mu of n squared plus 1. Nobody knows how to get their hands on this thing. The factorization of n squared plus 1 is a complete and total mystery. Okay? So on the one hand, you actually have to pull this off. And I won't say anything about this except to remark that the way that one does this is exactly to exploit the mechanism by which you make counterexamples to this conjecture about the average value of the Mobius function on a varying quantity. That in the function field case, there's a way to work with the Mobius function other than its definition. And there's nothing like that in the case of the integers. And by exploiting this other point of view, it's possible to get your hands on mu of a varying quantity, and you can pull this off. And I should just to conclude the discussion of this, I should say that it was exactly the desire to get this to work out that led us to find this particular family. You have to be very careful. This was specially rigged to make that calculation work out with a constant sign that has nothing to do with little t. Okay? So this is carefully chosen to make it possible to pull this off with no t dependence. Then you have to cross your fingers and hope that you can actually compute this and to actually prove this. Okay, that the rank, and it'll be opposite this. Yeah, right? I mean, if you got this to be -1 and the rank is 1, it's not very interesting. Okay. So this part, this is sort of, you sort of specially design E eta to make this calculation possible. But then you have to hope that you can figure out some method of actually computing the so-called generic rank. Okay? So I would say that by far the hardest part, the hard part, is to prove that the rank on the generic fiber is in fact exactly 1 on the nose, less than or equal to 1. Right? We know it's at least 1 because you can write down an explicit point and prove it has infinite order. So the question is, how are you going to prove this? Because the usual kinds of methods of bounding ranks of elliptic curves, they're designed to work over global fields. Q, such things. But this is not a global field. So the question is, what property of this situation is going to give us some control on the rank? So let me tell you an initial idea that we had to try to solve this problem, which we thought seemed pretty plausible to work, and then turned out to come crashing down. So we had to come up with a different idea. So let me first tell you a sort of very natural idea for how to try to bound the rank by a specialization argument. And then I'll tell you the disaster that ensued, and then come back to the successful method. So to do this, we have to use something special about our situation. And we're not going to be able to get very far by manipulating the equation, because the equation is some kind of unwieldy thing. Oh, I'm sorry, I shouldn't really have erased that equation. Well, I'm not going to really use it again. I'll just say that the only purpose, I put in a couple of constants, C and D. The only purpose of that was just to show that, in fact, you can make lots of these things. There's nothing, you could take that to be 1 for the whole discussion. So let me first discuss a sort of a first, ultimately unsuccessful attempt to bound the rank. Well, as was pointed out, the point 0, 0 is on the curve. That has order 2. Right? One can check that's the only 2 torsion point. So if you think about this group, at least locally at 2, there's a point of order 2, and then there's sort of ranks worth of, let me call this R. There's ranks worth of stuff. So if you actually look at this mod 2, then you just get Z mod 2 to the R plus 1. Okay? So to bound the rank by 1, we just want to show this is at most 2-dimensional. So we want to show that the F2 dimension, this guy, is in fact at most 2. Okay, so how are we going to do this? So here's actually quite a nice idea. So let me first, just to get some intuition for this, let's replace this by the rational numbers. Okay, so we're maybe on slightly more comfortable ground. Suppose I give you an elliptic curve over Q of t, and you wanted to bound the rank, right? Well, one thing you might try to do is, well, you might try to specialize capital T to be a rational number, okay, and try to get your hands on those. But there's another possibility, which is to try to specialize Q to be a finite field, try to reduce mod P. This is a finitely generated group. So each generating element, all right, it might involve some denominators, but there are only finitely many of those guys. So as long as you take a prime that avoids the denominators of a generating set, it makes sense to specialize this thing into characteristic P. Okay? And this is now a global field. All right? And you might try to, maybe you could do some kind of two descent argument, or maybe try to get your hands on this thing instead. Maybe this will be more tractable. So we want to do a similar thing here. So what's the analog of going from Q to FP? Well, this thing is K of U. So try to specialize U into a finite field. Reduce modulo a polynomial of kappa bracket U, just like here we reduce mod a prime of Z. Right? So here's the idea. First, let me just say something to get it to initiate why one might hope this would work. The Silverman specialization theorem said that for all but finitely many ways of specializing capital T into the coefficient field, the specialization map was injective. In fact, if you use a variant on that method, you can prove the same thing works. This is kind of like specializing in the other direction, not in T, but somehow in this thing. All right? One can prove likewise here that for almost all P, this map is injective. Right? And the same thing goes here. So one can show, by adapting Silverman's argument, that for almost all, I'll just say sort of points, let's just think over the affine line, or if you like, you can think about working modulo an irreducible polynomial, pi. Okay? But maybe pi might not be linear, right? This might not actually be a number in cap. It might really live over a finite extension that if you sort of specialize, maybe I'll write E sub U naught, right? We're sort of specializing the rational function coefficients in U to living in the finite field generated by U naught over this kappa U naught of T. This is injective. Okay, so this is in fact a true statement, and so, but now this is a global field, and so of course this is injective. The rank of this is bounded by the rank of this, and in fact one can show that this point of infinite order that we had here, when you specialize to here, again it always has infinite order. So you can just try to play the whole game on this side, but now the U has collapsed to a constant, so it will be enough to show that the dimension of this guy, maybe I'll call this EU naught of, let me just call this thing kappa naught, so I don't have to keep writing the U naught all the time, mod 2 is less or equal to 2. Right? And you think, oh, okay, this is more tractable because there are actually methods to, this is a nice global field, so maybe I can try to use some kind of standard 2 descent argument, try to actually manipulate the equations and get lucky and get a bound, at least for infinitely many points U naught, right? The point is, this may be, when I say almost all, I mean all but finitely many specializations, like here. For all but finitely many P, this is injective. Yeah? So for all but finitely many P, this is injective. So if for infinitely many times that you had a bound, then most of those guys would also be in this world here, and so you could combine them, and the bound on this would give you the desired result here. Okay? Now you think, all right, well, this is a very plausible idea, so how are we going to pull this off? Well, let me not get into how one would find the reasonable points U naught, because they'll rear their heads later on in the other approach that did work. But suffice to say, when you try to give the bound on the rank of an elliptic curve, life is easiest when there are fewest possible number of points of bad reduction. The more bad primes you have, then the more complicated it is to sort of use the descent argument to bound the rank. So what you try to do is try to choose the points U naught so that the number of points of bad reduction for this, the number of physical points of bad reduction, is as small as possible. One can isolate which such points there are. Chebytarov density theorem will provide you with an infinite collection that realizes only 2 points of bad reduction. And then you try to go into this, and then you run into the following situation. So it turns out that when you try to use the sort of standard sort of 2 descent method, so for the for those U naught making this elliptic curve EU naught over kappa naught T have the fewest
number of points of bad reduction, in this case actually 2, one finds, well, let's see, you have your, this is the guy we're trying to understand, mod 2. Then you have sort of a Selmer piece coming in here. And then there's this piece from the Tate-Shafarevich group in here. And you would like to say that this is oh, sorry, I have it in backwards. Then you have a Selmer group here. And this guy here, one can show that the dimension is, in fact, at most 4. And two dimensions of this are explained by an explicit subgroup. There's a certain two-dimensional piece that has nothing to do. In here, you have the things coming from 0, 0, and this point Q. Yeah? They both live in here. They contribute to 2 dimensions worth. And in here, you can find 2 more dimensions worth that have nothing to do with this. And so in order to know this is 2-dimensional, you just need to know that this other plane injects into this piece here. And so you're faced with the problem, how do I show that 2 elements of this map independently to different lines in here? Well, on the Tate-Shafarevich group, there's this so-called Cassels-Tate pairing. And so if you could somehow show that your 2 basis guys on this side mapped into here have non-vanishing Cassels-Tate pairing, then they have to be independent, and so you win. All right. So anyway, so I thought, and there's a paper by Cassels that gives a nice method to actually calculate the Cassels-Tate pairing on the 2 torsion of the Tate-Shafarevich group if you can write down a model for your elliptic curve. And so when I came across this paper, I thought, fantastic. All I have to do is understand this paper, which is actually not such an easy thing, and just calculate. And come on, of course I'm going to get non-zero lots of the time. So then I went around giving talks on this paper, and I just said at the end of the talk, I said, oh, and of course you do this calculation, you get non-zero infinitely often. All right, then I sat down to actually do the calculation. It actually always comes out to be 0. Suffice to say, I was not pleased. So this was actually quite distressing, because then it makes you concerned that maybe there's some extra point of infinite order that we haven't found. Oh, that would be awful. All right, so this method kind of died. So that's too bad. So you try to use, and then that's after spending a month figuring out what on earth is happening in Cassels' paper, right? All that time down the tubes. OK. Anyway, all right, so one needs a better idea. And I should say that somehow in here, one hasn't really used any geometric structure of the situation. Everything sort of comes from manipulating the Weierstrass equations. And, well, there is actually geometry in Cassels' method for computing the pairing on this. But suffice to say, it's not worth the effort because you don't get the answer you're looking for. All right. So we need a better method. So unfortunately, so the natural idea here, to get the injection, you want to know if this is injective, the natural idea kind of dies. All right? So that didn't work. And by the way, it doesn't, right, just because it's 0 doesn't mean that they couldn't have been independent, because in fact, the Cassels-Tate, this might be quite big, and there could be things coming from the 4 torsion, and there could be all kinds of reasons for things to vanish. So this doesn't work, but it also doesn't show that the thing can't be true. So you need a better idea. Or put it this way, you need to use more structure. So more geometry of our particular E. And now you're faced with the problem, which is, well, we just rigged the thing algebraically so the root numbers would come out. So now I got to look at this thing again and find some other magical property that this thing has. But it has another magical property. Or rather, it has a nice geometrical property that was not at all put into the design, but that turns out to be very well suited to bounding the rank. And we're still going to use specialization, but with a very clever trick. OK, and so what's the trick going to be? So in this kind of failed method that I described, we try to just specialize U into lots and lots of finite fields and hope to bound the ranks on that side. And now we're going to try a different point of view. So here's a better idea. So this is the thing that we're trying to understand, mod 2.
Right? I would like to show that this thing is at most two-dimensional.
So we had our failed approach, which was to try to specialize U into a finite field and kind of hope for the best. Well, actually, I should emphasize, we didn't actually study this map. What we said was that for most of the time, this guy injects into this guy, and in fact, you then just jettison this and focus on this piece here. Because actually, I have no idea if this is injective or not. All right, but you first studied the rank of this is at most the rank of this, and now you ignore this, and we focused on that. So on the one hand, you have the map from here to here, which kernel you don't understand, so that doesn't seem to help. On the other hand, what we could do is extend the constant field to an algebraic closure. And now you can, of course, stuff this into that algebraic closure. OK. Now, here's the trick. We would like to prove this is at most two-dimensional. Now, it looks like, OK, I've introduced 3 new things. I'm trying to give a bound on this. I don't even know if this is injective. What about that? There's nothing. But the Lang-Neron theorem saves the day. So before I mentioned this Lang-Neron theorem that you had a good finiteness property for Mordell-Weil over capital K of t, but that was really Neron's thesis, the real guts of the Lang-Neron theorem was even if you're over an algebraically closed constant field, as long as the elliptic curve is non-isotrivial, then in fact, this group is finitely generated, and each of the generators comes from a particular finite extension. So before we start analyzing the rank, let us first increase the constant field to fill up this whole group. Put it another way, so Lang-Neron says that the group of points over kappa u bar t is finitely generated. And therefore, it must equal E eta of kappa prime ut for some finite extension, kappa prime over kappa, which of course may depend on the particular elliptic curve. Right? Like I had those 2 parameters, C and D. Okay? Maybe it depends on those. Anyway, let's rename. After all, if this is equal to this, and the group we're trying to understand, the rank on sits in here as a subgroup. Of course, if I can control the rank of this, that gives me a bound on the rank of this. Let's replace the original constant field by a bigger constant field. I have no idea what it is, so that these, in fact, becomes the same. And if I can win there, then I'm in business. I must emphasize, it's very important here. Originally, when we tried to design this, we thought about maybe choose C and D so that something's a square or something else is not a square. And if you try to impose arithmetic conditions, that could, of course, be completely destroyed by increasing the constant field. It would be a complete disaster. So we, in fact, avoided that. And so if you increase the constant field, you can rig it so this group is the same as this group. So this would be an isomorphism. Okay? Now, why is that useful? We would like to prove that this thing has dimension at most 2. Okay? Now, this diagram commutes. So this is the same as this. So this here, you can think of this is sort of geometric this is sort of specialization in a geometric setup. Over an algebraically closed field, which is to say we really have sort of over P1 cross P1, we have it's sort of a 2-parameter family of elliptic curves. We have some elliptic curve E eta over kappa bar ut, right? And what we're trying to ask is, let's specialize this u into the constant field. Perhaps we're going to try to show a geometric part, so the geometric statement, which is that for all but finitely many, points in kappa bar, this is injective. I will state this more precisely when I get to the next board. But roughly speaking, I want to make an injectivity statement for this map in a geometric situation for all the finitely many specializations. And here's going to be the arithmetic part. and then we'll see how they link together, that this map has image with dimension at most 2 for infinitely many U0. Which ones will come out of Chebatarov? Okay. Now, suppose you could rig this. Suppose you could prove a geometric assertion, which is that if I give you an elliptic curve or maybe an abelian variety over a field like this, subject to some property that I haven't stated yet, but it has to be some geometric property of the bad reduction locus for the elliptic curve or the abelian variety over this surface, subject to some geometric property that hasn't yet been formulated that will hopefully be satisfied in this situation, that there'll be some criterion on the geometry of the bad reduction divisor that will guarantee that this map is injective almost all the time, for all but finitely many times. And at the same time, there's going to be an arithmetic claim, which is that for infinitely many U0s on the affine line over kappa, that the dimension of this image is at most 2. All right? Now, if we could rig this, we win. Because on the one hand, this guy is injective with only finitely many exceptions, but it factors through this, which is at most 2-dimensional image with infinitely many times. So therefore, infinitely many of these will fall into this setup. And so therefore, this injection will have at most a 2-dimensional image. And I've completely avoided the problem that I still have no idea how to settle, which is whether this map is injective or not. Okay? So this is the idea. We're going to break the problem up into 2 separate parts that have nothing to do with each other. There's going to be an arithmetic part, which will actually involve a careful understanding of the arithmetic of the original elliptic curve. And there's going to be a geometric part, which will involve something about the geometry of the bad reduction divisor. Okay? In fact, this is the strategy that does work. And so let me just tell you very briefly what is the geometric property of this that makes the geometric part work out, and then I'll conclude with a few comments about the arithmetic part, and then I'll end. So I'll just do this in a few minutes. Okay, so what is the special property of this? So we'll look at P1 cross P1. So think about this as the kind of the U line and the T line. And you can ask, what is the largest open set in P1 cross P1 over which E eta has good reduction? That you can kind of extend it out to a nice equation which reduces nicely with no poles or vanishing discriminant problems. What is the biggest open set over which you can do this? For example, if you look at the original equation as it's written down, okay, then if you stare at the coefficients of the A of t and the B of t, it involves u and t, and you write down the delta, okay, the condition that these things have no poles and the delta does not vanish, that this is complements to certain or rather the conditions that things do have poles and the discriminant does vanish, these cuts out certain divisors on the surface. And as long as you're away from those, you're in business. Now, it may be if you find a better model for the equation, you might remove some of the divisors, maybe not all of them. But the point is that there are going to be certain bad reduction divisor. And it turns out that in this particular case, if you study the situation, in the bad reduction divisor, there is one vertical fiber at infinity, and all the others are non-vertical. Okay? So this is a special property. That the bad reduction divisor, well, there are 2 properties. First of all, has, in fact, exactly one. What really matters is at most one. Exactly one vertical fiber, vertical component. And the other thing is, at the generic point of that component, which is some codimension 1 point on the surface, the reduction type is, in fact, potentially good. Over a tamely ramified extension. The 0.00 saves the day if you like characteristic 3. But anyway, let's not dwell on that. This is something which you have to actually just get your hands on the equation of the curve. What's the reduction type and work this out. So this is a property.
And that's, in fact, the key. That, in general, if I give you any, you could think about this as a surface fibered over the U line. Okay? And in fact, if I give you any surface fibered over P1, and I give you any abelian variety over the function field of the surface, so that the bad reduction divisor has these two properties, that it has at most one vertical component, and that at the generic point of that component, the reduction type is potentially good over a tame extension, that this guarantees that, in fact, the right-hand side is injective with only finitely many exceptions. And I will tell you finitely many exceptions. And the key that makes it work is that in positive characteristic, the affine line has no unramified covers that are tame at infinity. Art and Schreier theory gives lots of covers that are wildly ramified at infinity, but if you insist on tame ramification at infinity, that the affine line is simply connected. Okay? And that's the key geometric input that makes it possible to prove this. So in fact, that's the geometric input, that this particular thing, it has a property that's not obvious from the equation, but if you look at the geometry of the bad reduction divisor, it has this feature. And that makes this, and there's nothing special about 2. This, you could replace 2 with any n that has nothing to do with the characteristic. Okay? So this is a general principle that works for any abelian variety over a fibered surface with that property. So that takes care of this part. And I'll just say for this, in one sentence, you have to use Chebatarov plus the arithmetic of the neuron model, or no, there's the reduction structure of these EU naughts plus a calculation in Tate homology. And this gives the result. Which is to say that the points U naught that you choose come out of something using the Chebatarov density theorem. And then for those points, you can describe the neuron model, the reduction structure, quite nicely. And then the question of whether this is injective, you stick it into a well-chosen exact sequence coming out of a Tate homology, and you can analyze the term over here and prove that it vanishes, again, because of special properties about the cohomology of the projective line. So ultimately, you win. But I think this is sort of the novelty of it, that you try to specialize and it doesn't work. But if you specialize in sort of by exploiting the Lang-Neron theorem, then you break the problem up into these two parts that you can treat in completely separate ways, and magically in the end it works out, and so you get what you want. Okay, so that's why the rank of the generic. It sort of sounds like a weak, kind of a minor statement when you say it by itself. Oh, the rank is 1. Just calculate. But it's hard to do these things over k of t, because I should add that if you work over, if you might, and it's very curious that, usually there are geometrical bounds given the geometry of various things, but these bounds are horrible. If you apply them in these cases, standard upper bounds on the rank coming from the geometry of the bad reduction locus, they give horribly big bounds that depend on p. It's just useless. So you have to use some arithmetic input too to show that in fact the rank is exactly 1. So anyway, I'll stop there.
Can you do something with these things to produce ellipticals with big ranks on Q?
I could tell you, but I'd have to kill you. No. This says nothing. This doesn't tell you anything. Because notice, like here, I haven't said anything about, and I think in all of these things where people use the parity conjecture, I mean, nobody can find, you can't use this to find extra points, because after all, the only point of infinite order I produced was the one that came from an algebraic formula. And so it's not going to really, I don't think it's going to help. Certainly not in this. The rank was 1. Yeah.
Is there any reason to not believe this density conjecture in this function field case?
No, I should, maybe in a positive direction, this reminds me of, there is something called Nagau's heuristic, which there's another heuristic due to Nagel that makes predictions on the rank of the rank of the generic fiber in terms of ranks of special fibers and so forth. And if you just do the numerics, actually this thing seems to fit into this Nagel heuristic. So, which doesn't pertain exactly to the density conjecture, but at least other conjectures on trying to relate the ranks. I mean, this one numerically seems to fit the prediction.
So you wouldn't expect the rank of the special fibers to be any more than one more than the generic fiber.
But again, there's no basis. I mean, the Nagel thing really amounts to you have to specialize things over lots of finite fields, and do some sum of, I don't know, one of these analytic number theory Dirichlet series thingies. But in this case, no, I have no reason for an expectation or extra points or anything.